one update from this, and it was kind of in the chat. We have that sheet for the chemistry. We are looking at it from a form factor perspective. The big crux of the issue with doing a form factor perspective and a pack perspective is the cell design and chemistry are really going to impact those, right? And then it's also, what do you value? So for example, cylindrical cells are quicker to manufacture than pouch cells. I'm just going to say that out loud, and that's kind of an unfortunate truth, and that's why you see everybody going to cylindrical cells. And then to the question here about silicon percent, it means the quantity of silicon relative to the amount of conductive additive and or graphite inside of the electrode.
Yeah, and one of the things we made very clear here was that this was basically majority silicon, which I would like to caveat, no one is really doing yet. People are doing a lot of development, there's a lot of announcements, but there's nothing commercial yet, right? The example would be the Silinano Whoop Watch, which is about 20% silicon in the anode.
It's really hard to get above because the electrode starts degrading on itself. And then also for a lot of the silicon companies, they're fighting the yield/consistency paradigm, which is like, it's really easy to make something in a small beaker and have it perform pretty homogeneous. The moment you scale up to like tons, it becomes really hard to control particle dynamics and especially the synthesis routes. So then that becomes an issue.
And it's one of the few places where you really do see a big difference between companies making the material and companies building the cells. So simple example, Silinano Group 14 making silicon material that they want to manufacture in high quantity. And you see companies like Stordot and Ferrosys who are buying the silicon materials and using them to make the cells, and they're just focusing on the cells, not the material.
Yes.
So they're very different problems, and it's hard to do all of them. And there are companies doing all of them, like Amprius and Enovix, that have their own process for making the material and process for cells. And basically, those are kind of the four biggest players.
Yeah, and as far as the report for the beta or the structure for the beta for the pack and the form factor one, guys, we're not releasing. We don't like to release beta stuff. Like, this has a bunch of revs behind it.
I was just going to say, and we had a lot of people help us with this, but basically, like, every single one of these boxes represents tens of minutes to hours of work. And I mean, just something as simple as like, where did the cost come from for the LCO? And it's like, you go to these comparison tables, we went through hundreds of reports and hundreds of cells and a whole bunch of other people's data, found the highs, found the lows, double-sided sources, went and found, here's just a simple example, but like just a bunch of links for each type of chemistry, a bunch of general ones that compare them against each other. So there's a lot of substantiation, but there's also a lot of ways that we can be wrong because it is really comparative. And so again, there's a giant bunch of caveats down here about how we did it and why. And any feedback from the community we'd really appreciate. And there's a form to give it to us.
As far as and then kind of back to the questions. So this one's easy. What is the best energy density you've come up with so far? If we're talking about something that is sold on the market, I want to clarify that you could go buy it today. Aubert and I can go make batteries with stupidly high energy densities. It means squat because I can't sell it to you. Nor would I.
Yeah, it'll go 10 cycles and then blow up and kill you.
Exactly. we aren't savage human beings. So the best we've seen, it's LG's MJ1. Go look it up. It's a cylindrical cell, 287 or 280, somewhere in there, watt hours per kg. And it'll give you 1,200 cycles. It's currently what they use in aerospace. You pay a premium for it. But that is probably the best commercial cell you can go buy. That is like a reasonable form factor. There are more energy dense materials. You can get prismatics, but those tend to be like the size of your head. And that doesn't really lend itself to great applications or small form factors. So the MJ1 is what I would go check out. And then the next one is for like a post lithium world, guys. I don't think there is a post lithium world. I think there is a acceptance that lithium will not be the only player or market share. I think magnesium will make its way. If you look at $500 million invested into Form Energy, they're doing iron air for grid storage. That's a great example of there's no lithium, there's none of that. It's just iron and air, which is abundant.
And the acceptance that basically they have great cycle, great low cost, but it takes a ton of area. It's very heavy. So it's never going in something that's moving. But if you've got a lot of space, it's a very effective way to do grid. right? And I think there'll be a lot more focusing on stuff like that, where it's not a one chemistry can solve all the problems. It's a targeted, this chemistry goes in this application because it meets the biggest requirements. And for grid, the number one requirement is kilowatt hours per cycle cost. That's it. That's all they care about. They don't care about the space and safety, sure. But like when you put a big battery pack in the middle of a desert somewhere, you know, if it blows up, it blows up.
Kate brought up a great thing. The MJ1 isn't great at high C rates, guys. I'm not going to give you a 6C 280 watt hour per kg battery. I think you'd have better luck finding an elf in a pot of gold at the end of the rainbow. The reality is cell design is going to be dictated. I picked something I knew had it, or had the highest. But as far as like stuff that seems impossible, like some of the newer technologies, as somebody who works on lithium metal, there are ways to get there. If you guys look at it this way, like think of the last 30 years of technology advancement. So like there is work, it's just time and how much time you're willing to spend on the chemistry to get it fixed. And a lot of people spend time. Think about sodium ion. That took ages to get to high cycle life. And that has a lot of similar tangential problems you actually find in lithium, which is sodium is highly dendritic forming inside of the cell as you cycle it.
I would love to ask a question if I could on slides 52 and 53.
Sure.
And for a technology like LFP that's pretty mature, if we can call it that, is there any research you guys have done on, now that LFP is coming to North America, what is the process, or maybe the new improved and environmentally appropriate process that we should be doing in North America versus what's done today in China?
Oh, that's a great question. You know, Jeff and I probably have some qualitative things we can say, but at a high level, you know, at least we kind of both know the cell chemistry piece, and we know kind of as things come in and where things go afterwards. So what I can say about that is basically recycling is going to be really important. Local supply chains are going to be really important, just because the farther you have to transport things, the more pollution it makes. And the energy used for the manufacturing processes, I think, is really critical. And that's something people don't talk about as much. So like if you're getting processed graphite out of China, it's probably made with coal. So it's really dirty to do that. And if you're getting it made with solar somewhere else, that is better for the environment. In general, especially for EVs, because they're basically at this point lithium ion batteries, if EVs do not recycle their batteries, it is profoundly worse for the environment than gas cars over the lifetime of the car, if it's only like used for 5 to 10 years. And without recycling, it actually doesn't pencil out from a carbon footprint perspective.
Yeah, and to kind of be frank, I know Bob earlier said 99% of batteries in China are recycled. That's not the case, unfortunately. We can't even recycle it here with the best technology. The issue, the core crux of that is primarily coming from getting the correct technical grade that you need for batteries out of the resulting materials. It's very easy to extract the carbon. It's very easy to extract the metals. It's pretty easy to extract the ceramics. The problem is they all come out in slightly different corrupted and or degraded forms, and getting them back to the correct technical grade is highly expensive and not cost effective. As far as the systems in place for LFP that you need to worry about when we bring manufacturing back to the US, the real answer to that question is we need to figure out how to mass produce it effectively. There's about 2 companies in the States that do LFP. One of them is in Texas, and their name blanks me. And then I think
Redwood
Materials does it. The problem you have with those is you can get better materials elsewhere. And the reason being is the US has to put a system in place where they're willing to dump billions of dollars into a battery manufacturing facility at size and at scale in order to actually spend the time to do the development work to figure out what the correct particle size distribution, purity, et cetera, is for those materials in order to pipe them in. Until then, we'll just buy from elsewhere because it's just better.
Yeah, higher quality and cheaper. So what I threw up, I've been flipping through the recycling slides, and I apologize for going so quickly. I forgot where things were in that section. But if you go to page 100 and something, you can see all their slides on recycling, and they did a really good job here going over basically what is needed, the processes, the costs. And one thing I just kind of want to highlight here is amount of scrap and year, and kind of where the sort of crossover might be. So like the point where recycling is going to be a significant contributor to materials is very far out. And an easy way to think about that is basically EV production is going up each year, right? And when you recycle something, so if you're here in this year and you've made, on the graph, this many EVs over, that year, you're recycling the ones from here. So there's this many total of them, and you're recycling this many of those. So when you look over here on the graph, you're recycling this many that year to make this many that year. And until basically kind of the supply all kind of stabilizes, it's not going to be a major contributor.
Yep. And that's the reality.
Yeah, and I think even just the processing of the cells, or even the raw materials that go into the cells, emit air, emissions, waste emissions, all of that. And if you guys do start to look at that in your analysis, let me know, and I'm happy to help. I'm already looking at it for my company as well.
Sure,
Yeah,
sure, love to. That's something that's very interesting. It's just Jeff's going to get into manufacturing pretty soon at Lighten.
Oh, no, I mean, I'm already there, but like it's the problem with manufacturing, and the problem with anything else is it's just inherently cost prohibitive, right?
Yeah.
We can, I think if everybody wants, maybe Google Maps still has it, but if you look at the Austin Gigafactory via satellite view, you will see they have like essentially mountains of scrap behind the factory from where they have been trying to get their manufacturing processes in alignment with what the actual like specs call for. And that is just like, if you think about it this way, like you turn a line on, you're going to spend probably like $500 to $1 billion. So the better way to even say it is, if it costs you $3 billion to make a gigafactory, expend another $3 billion on people and scrap just to get into the correct yields.
But if we set it up right, North America, I think the scrap can be someone else's gold mine, right? For what they do. So like even some of the trace materials could be fertilizer, from crops or, I mean.
Yeah, I think there's that. And then I also think there's the reality of like, how do you set it up in the US? So the biggest thing for the US is like, for example, we have a lot of lithium, right? Like I think it's something like 70 ppm per like pound of material of the earth is lithium. So there's plenty here for it. The biggest problem with lithium is just to get the brine to maturity. That's 4 years, right? That doesn't include the to your points, that doesn't include the like environmental impacts and the zoning and everything else. So to get a brine to start, it's like 4 years of the brine actually existing and doing things, and then probably 3 years before that of just trying to get the place built out, meeting regulations, meeting zoning, all of that stuff.
And setting up the production, ordering the material. Yeah. So.
And then once you get the brine done, you then have to figure out how to make it technical grade. Yeah. So then you get another couple of years of just figuring out how to best pull the materials in order to get it into the right technical grade.
That's why the manufacturing group loves this stuff too, because it's like, well, okay, now that you figured out the great idea for the battery, how do we make it happen? So it's a good partnership.
The thing that I'm kind of happy about in a lot of ways, the price increases are kind of making people be more long-term rational, basically, with the fact that these are now, oh, right, they're actually scarce, expensive resources. There's not enough cobalt to make all electric vehicles out of. Okay. But the fact that it's so expensive means you almost have to recycle now. Whereas if they were using plentiful materials and it wasn't economic to, they just wouldn't. Yeah. It's just a simple fact, right? You can't incentivize to people to do something that's not economically viable. So the fact that the costs are going up so dramatically and the supply is so limited right now, I think is really good, because it forces people to be recycle. And so we'll see that going forward being more of an issue. And I think also you'll see the regulation and a lot of incentives around the world to recycle more, because people actually are going to want to control the recycle streams of batteries as a material supply, which you mentioned earlier, right? It is somebody else's gold mine once you get it set up and working reliably. Yeah. Now, one of the biggest problems, though, is that you can't make one recycling facility for all batteries. You have to make one recycling facility for that gigafactory's batteries, because you have to know how to take the packs apart and get the cells and what materials there are, and the form factor and the layout and the construction of the cell can make a really big difference.
I think that is very true from a cell design perspective, but I think what's going to be more interesting in the coming years, I know Bob said we'll see a lot of like battery to frame integration for a lot of the vehicles. I think that's actually going to come to heads with the current right to repair. They're like, I'm not speaking any of like forecasting on which is correct. I'm just saying there's also a large movement of people who are incessantly pissed off that can't change their batteries. And there is a movement of people who are looking at how to cost shave as effectively as possible and drop materials out of the things that they are building. And they will soon butt heads with each other. Right.
Yeah. And there's basically kind of two approaches. And one of the approaches is you build the battery into the chassis of the car, which saves you kind of cost and weight, right? So that's a pathway. The other pathway is you have some kind of swappable battery pack, or, and this is a very kind of new idea, you have a swappable car with an evergreen battery pack. So if you look at stuff like Jeff Dawn's work, if your battery pack can go 1,000,000 miles, that's a lot of cars. So you could be replacing the car around the pack and the frame every 5 or 10 years. But that has to be built in. And that's a very different business model, because that pack will be worth a lot more than the packs today.
Yeah, and also you have to take into fact it's in a company's best interest to make money or increase revenues and also sell things. And if you create something that goes 1,000,000 miles on the road by itself, that is actually adverse to what the company goals are. Because what is the incentive to upgrade the thing that surrounds the pack? You're either rich and you have money, or you don't.
They use a lease model and they retain ownership in the battery, and they lease it to you for X dollars a month, like a subscription service, and you get to put whatever car you want around it. But again, nobody's actually planning to do this. This is very like hypothetical going forward ideas.
I can see all the VCs in the chat with their pencils and papers going down right now, just writing this down.
If you raise $1 billion on this idea, I would like credit, please.
Yeah, I don't need the actual money, but if you could just do it, that would be great.
Just a recommendation on LinkedIn will be good.
So I'll go through some of the names. It looks like we have some hands up. Anne, you got your hand up?
Yeah, that was, you guys answered my question.
Okay.
Thanks much.
And then Felipe.
And real quickly, for everyone else, like, this is pretty informal. You can feel free to just
type it in chat. I'll get to you. Yeah, go for it. So Felipe.
We'll just keep talking until someone interrupts us.
Just a quick question, a bit technical, trying to understand. So I once spoke to a researcher, and he was telling me one of the barriers for solid state batteries is also high temperature for ion diffusion on the separator, well, on the material. How is that going to affect battery design? Because instead of building battery packs that have to work at 25, 30 C, we're talking on some applications, maybe 80, 90. So and it will be interesting to see if the cells that you're kind of pushing on what is the temperature they're supposed to work for better performance, for example.
Yeah. So
it's actually very interesting. Yeah, there's a lot of work people are doing to look at how you can get higher temperature performance. And right now with liquid electrolytes, basically above 50, 60 C, they crap out. It just doesn't work. So you have to use it depends on the electrolyte. But basically there's a lot of work going into things like ionic liquids or high temperature electrolytes. And when you replace those with a solid state material, you can go at higher temperatures, and actually lithium metal batteries work better at higher temperatures if the other components work. Right now, it's the other components that crap out.
Yeah. So also you got to look at it from the standpoint of this is already being solved today. So there is a reason why electric cars get severely diminished range when they're in snowy climates. And that is because even though the cell isn't meant to work at like -10 C, what it can do is provide very little amounts of current. So what the cell will do is discharge very, very slowly to a heating unit, which is built into the battery pack, which then gradually starts heating all the other cells to get them up to performance. So if you're talking about how you would integrate a solid state battery, it'd be the same. You would start at 25 C in like your local climates. You would take very small amounts of current to start heating the pack up, and it would essentially take part of its capacity to get the whole pack up to the correct operating temperature to increase capacity. And that's kind of how cars do it today in cold climates.
So would you consider, one of our cell providers is, I got an offer of low temperature LFP cells that they can operate below zero without the impacts that the standard LFP has. If you wanted to build like vehicles that operate mostly on sub-zero temps, will that be something that, if it was your choice, would you consider putting on a kind of commercial heavy duty vehicle to save some on the inside?
I don't think so. I think I'd still go with the heat the normal cell up design built into the pack. The ultimate goal, right, for a consumer is to have as much flexibility as possible, right? Consumers are inherently terrible people to design for. And what they want is the greatest amount of bang for their buck. So the problem with doing a low temp cell is like if the consumer is like, oh, I'm going to road trip from like Alaska to California, the odds are the pack will have to work really hard to keep those cells in the correct operating range, because low temp cells, generally the electrolyte is tuned for that, and they flip the inverse direction when you get to high temp. So like if 50 to 60 was the correct operating point for that cell, right, it might be 45 C now, and you just lost 5 C of your headroom. So the pack has to work a lot harder at higher temps in California. So it just, you don't ever want to geo lock someone with your technology. That's usually not a good rule of thumb.
And the final question is, the Excel spreadsheet that you were building is quite with a lot of information. Maybe I didn't catch, I haven't seen it in depth, but suggesting depth of discharge kind of windows for longer life in terms of based on testing, that will be interesting to see.
Yeah, I can do that. That's a fun one to do. Basically, here's a good rule of thumb, everyone, if you've ever done it. Yes, not discharging your battery below 50% doubles your cycle life, but every 0.1 volts you take off your charge doubles your cycle life. So think of it this way. If you start charging to 4.2 and if you charge to 4, you have quadrupled your cycle life. That is the better rule of thumb. That's why you see Tesla owners always go between 20 and 80. And that's because it kind of corresponds to the voltage window. But that is also because if people know this, you know that there's a lot of pop cells in Teslas, and that's why their range tends to diminish pretty quickly. So you see a lot of extra care around that.
And also the higher rates, even if you stay within 20 to 80%, the higher rate you charge and discharge in general, the quicker you degrade a battery. It almost doesn't matter what kind.
So LFP in the chat to Eric, LFP is getting traction not because of its performance. LFP is getting traction because it was cheap and it was perceived as inherently safe. It is no longer either of those things.
It was perceived as safer, comparable in performance, and much cheaper.
Yeah.
And basically it is no longer cheaper.
Yeah, it is. And the reason it has continued to gain traction is because there is a snowball now that is just money being thrown at it, and people are following the snowball of money. So like right now, NMC is just as effective cost-wise as LFP, and you get more performance. So why wouldn't you just build NMC? Well, the reality is a lot of people are starting to continue to just build NMC, but they want to keep pumping that they'll do LFP, so they keep getting the investment money to build out those lines.
So there was an LFMP question, and so I'm just going to jump over to here. So that's not my expertise, but the answer is the reason people are being interested in that is because it's basically a performance increase on LFP, right? It's some different performance performance with some different cost structure or manufacturing availability, and so it's the same thing as people doing the difference between 811, 622, 111, 523, NCA, NCMA for the nickel and cobalt materials is, oh, there's just a different combination you can do, add something else, subtract something else to get a different performance at a different cost or availability.
What you're seeing really is people starting to diversify that chemistry, that's spindle structure into like its various components, because maybe it's just cheaper to build out 2 of the materials than it is the other, or add this material, right? Like people who make magnesium have a vested interest in making sure magnesium is sold as much as possible. And if they can prove that magnesium adds performance value to LFP.
And the other piece is magnesium's still relatively cheap. And so a couple of quick questions in here. Yes, LTO is still manufactured. It's just less than it used to be. And Jeff, Bruce, thank you for saying that. So this is something that Bob made a point on, and I wish he'd elaborated on more today, is basically he went, there's old people like me who've been here forever that know what we're doing. And then there's young people that don't. And the very typical thing you see in batteries is that every 5, 10, 15 years, to your point on, LFP was done by, Valence and A123, 15 years ago is about when they did that. And then it didn't work. And now somebody came up with the idea again. And technologies in batteries are very cyclical, where somebody did it, it didn't work, the company died, and then 5, 10 years later, somebody else picks it up again. So like you'll see lithium air, aluminum air, stuff like that, where People have been trying to do that since the
Yeah.
80s.
Like, and also guys, towards the safety aspect of it, guys, let's not confuse ourselves. Yes, a 90 kilowatt hour battery is fantastic with NMC. Even if you're like, oh, well, LFP is safer, a 75 kilowatt battery is made with LFP. 75 kilowatt of hours of energy is still a lot to have under your ass in a moving vehicle. And if it goes boom, I guarantee you it is still going to kill you. Like, the difference of the safety magnitudes, it's like saying somebody who rides a motorcycle versus a car. You're like, well, the car is safer, but guess what? The car can still kill you. Like, you aren't really making a huge trade-off.
Hey, Jeff, do you have any words to say about titanium niobium oxide? I just don't know enough about it to comment on that question.
Niobium doesn't have the supply lines in place to make it a reality.
Okay.
That is the short of it.
I know that I know from a PVD perspective, you can do thin film coatings of it that have substantial benefits, but those are not going to be used in EV batteries, for example. It's too expensive and slow a process, right? When you take semiconductor grade technology and coating processes and sputter targets, you can use them for very expensive, like thin film solid state batteries, for example. But I would guess that you're not going to see that outside of very niche applications.
To the comment, I'll ask this about cycle life being dismal for lithium sulfur, guys. So kind of just like a general comment about applications and chemistries, guys. Everybody here is focused on 1,000+ cycles, right? And that's because we all think of EVs. The reality is you need 150 to get your product into a market that is a high energy density market. You need 150. The government doesn't care. Government takes batteries at 6 cycles, 10. It goes on a special ops mission. The guy chucks it and gets rid of it. Why does it need more than 1 or 2 cycles? Like, you're everybody here, I think, is clouded, and this is something Aubert and I preach, is that there are several applications that have very different design characteristics that need very, very different types of chemistries, and there is going to be a chemistry for every application. That's just the nature of it, right? And you will get those eventually, right? DOD, the Pentagon only says you need 215. Like, there's another one. Aerospace is 300. Like, there are stuff, but you don't really need more than 500. You can get into a lot of stuff. Like your cell phone. Your cell phone is like over 200 nowadays. It used to be 115. And the reason for that is they need you to buy a new one every 2 years. Why would I make a cell phone go 1,000+ cycles?
Yeah, but I don't understand. Like, you have here, for example, that heavy duty trucks can use lithium sulfur. But, you know, I mean, even if I think cost wise, it's probably not as expensive as some of these other ones, but still, right? Like, for the whole battery pack, what the consumer or the customer is spending, how do you justify, you know, if it fails after 200?
Well, I mean, my counter question to you would be, is there a better chemistry? And if you say NMC, how do you make a 50-ton truck drive on any road? A planned amount of distance, right? Like, the reality with the truck one is there is currently, and you can look at the EV battery Tesla trucks and all of those things, they get about 100 miles max. And it's because they hit a certain threshold where they literally cannot drive on the pavement without destroying the thing they're driving on.
Yeah.
Oh, wow. Okay.
So, like,
so
right.
That's actually, that's a really good point. And just, I want to highlight that I think that's a great example. So thank you for bringing this one up, which is, if you notice, every other line is poor or bad. And the goal is just to highlight that maybe that one is slightly better. It might only be average, or maybe it's poor plus, but the idea is that they're all really, the ratings are comparative to each other as best as we could. And a lot of the other ones fail from some other reason. Maybe that one could, right? That's kind of the way this is done. And this is a great example of, like, if you disagree,
write a comment. We allow comments. Yeah.
Remember that this is S54, and you would go down here, you would click this link, and you would go, data your comment, here's who I am, here's what I disagree with, here's where it is, here's a link I found that says that you're wrong, Aubert, and I will go read it, and I will, if I'm wrong, I'll fix it.
Look, we are not ashamed to say we will backtrack on a previous statement. We come pretty surefire on things across, but, like, the reality, guys, is if we are wrong, tell us. Like that is,
and there's an enormous amount of information on this, and we did the best we could to basically fill in all the boxes as best we can. But a lot of them, again, they're comparative to the other things in the other boxes, and sometimes those won't be accurate.
and then to Guliamu's comment towards the spreadsheet, guys, cycle life is full DoD. So like in a residential grid storage application, you're never doing like full DoD. You're doing partial a lot of the time. I'll give you an example. I just spec'd one out for my parents and did their whole solar thing, and they roughly use 30 to 40% of their pack on a daily basis. And they don't go all the way up, so they'll probably get 4 times that cycle life out of it.
Mm-hmm. The other thing, just to backtrack back to the trucks and lithium sulfur, for basically all of these chemistries over here, we highlight that they're not commercial. And again, as best you can, you take announcements, public declarations from companies and papers, which a lot of times maybe have better performance specs on a like lab scale or pilot scale than they ever will when they commercialize. Yeah. And like, we just did the best we could to try to make them consistent and accurate. And so, especially with the, like, I can think of batteries right now that I know people are doing R&D on, where 2 types of the same sort of similar grade of things, so like, you know, the sulfidic ones, one would be poor, one would be great for a lot of these different ones, and it overlaps depending on what the materials are, and what the design is.
Part of the exercise in doing this sheet, everybody, was just we wanted to push that other chemistries exist, and we had to look at it from an if it did exist in market, but we had to also say it's not commercial, right? Like that's why it's up there. But it's like, if it did exist in market, how would it perform relative to the other things? Because a lot of the reason some applications are hindered is usually the weight. Like the reason you don't see a lot of like eVTOLs right now that carry a lot of people, or like commercial jets that carry a lot of people, is because at the point at which you get the energy density going, you start running into issues where like, no matter how many more batteries you add, you run into this problem where the weight you're adding by adding more batteries depletes the amount of energy you've just added to the pack. And you get into this like cyclical cycle. A good example of this is like the Hummer EV, which is like a 9,000 pound behemoth, but it only goes 340 miles. Yet you can buy like a Ford Lightning and get the same miles, but have half the kilowatt hours. So like you run into this game where even if you're adding more energy, you're adding more weight, and to move that weight requires more energy, and you run into that self-killing cycle.
Hey, Christian, thank you so much for that. The 2 people with their hands raised, why don't you just speak up right now?
Yeah.
Hey, I've got a quick question about whether for the discovery process and the process from discovery all the way through manufacturing, there's a lot of, I guess, repetitive or relatively repetitive lab testing that's happening, is my understanding. I'm curious if there's companies that are using ML to predict outcomes, and like who's doing that, and if not, why not?
So here's why not, is because to do anything predictive for batteries where it's chemistry, not just physical thermal properties, not just cell swelling properties, not physical items, it's the actual cell chemistry interactions with so much complexity. The answer is because when you change one thing, you don't then have the big data set that tells you what it does. And all of these new chemistry sets that people are doing, they're new, so there's no long-term data on what happens when you do anything with them.
Also, also just like the counterpoint from the science side, right? If you're looking at it from a fundamental science basis, if you look at it, it's really easy for me to say, I have this distance of material, it has this diffusion coefficient, it takes this, and you can create models that say, if I put all these things together, what are the parametric values or variables, and how do they impact the system? The problem with that is parametric values don't tell you cycle life. And parametric values, right? Like you can't say like, I put together this known particle size distribution with this known thermal diffusivity and ionic diffusivity and conduction, and it results in this cycle life, because chemistry is a spontaneous thing where you have reactions occurring sporadically throughout the electrode. It's kind of like saying using machine learning to predict how to manufacture nano-sized particles to be all exactly the same. When you get to like nano manufacturing, everybody's always going to tell you it is very hard to control the thermodynamics of those processes at such granularity in such large things.
Yeah, the high level answer is it's hard to use modeling to predict batteries when you haven't built a lot of that type of battery yet.
Mhm.
And there's lots of individual things you can model, and people do a lot of work modeling the thermal characteristics, and especially on the pack level, a lot of work can be done in the, the fluid exchange for the heat pumps and how the tabs, heat up and the conductivity changes as you gather all the tabs from the cells together and the big tabs that go into the packs and stuff like that. But I have not seen for new development, especially anything like a solid state or a silicon, I have not seen a model that is predictive. I've seen models where they take a data set and use it to come to a conclusion about what direction to go, but that's just basic, like, you shoot a bunch of design of experiments against a wall and you circle the one that worked and you iterate on that circle, right?
Mhm.
So I hope that answered your question,
Yeah.
Lauren. And who was the other person? Was it
Jeff.
Bruce?
It's the
Yeah,
other
yeah.
Jeff.
I got a couple of questions here. One is just commenting on the energy density of solid state. We need to include the infrastructure needed to make solid state work as well, not just
Yeah.
the cell itself, because it requires a lot of clamping apparatuses to hold that sucker together. And that's kind of why it's dead in the water for us from the consumer side. And I'm going to talk about consumer a little bit. And yeah, most of your audience is probably going to leave now, but
Everyone stay.
the other
I
one,
promise you.
the other one,
just real quickly, I just want to caveat, people who have a specific expertise in a market that looks at technologies from that, like you would have it at products at Microsoft, Bruce. We love talking to people like you to get the little dirty pieces that we can't find when we're researching it generally. So please continue.
Yeah, understand. Other one on recycling, that's something that we are very heavily involved with. And, we have the technology, we've gotten recycled cobalt working, it's great. Our biggest problem is the source. Yeah, a lot of people just gathering the material back. Right? People have a lot of, they got 5 laptops in their drawer somewhere. They're just not giving them up. These are things that are really hampering that recycling effort from our side. It's just getting the material back in. Our cell suppliers, that's their biggest beef, is they can't get the material back into the system because of the collection process. I think that's going to need a lot of work in recycling side. The other one is the cycle life. I love Jeff's analysis on the iPhone. Yes, cycle life, it doesn't really matter in the consumer side. When we look at our in-field telemetry over a 3-year period, our laptops get cycled 150 times. Yeah, so it's like, so that question now is, why is the EU now requiring 1,000 cycles? To sell into the EU in 2027, laptops have to have 1,000 cycle requirement, right? These are things that are.
I was gonna say, it's because politicians are not scientists and they make decisions.
Right. Yeah, so we're going to spend money to create a battery that goes to 1,000 cycles, even though when we see our in-field telemetry, the user's not using 1,000 cycles. So it's quite frustrating. Great. I love this table here. I do disagree with you on LCO. LCO is by far our highest energy density chemistry that we've ever looked at from our standpoint. It is something that we are, will continue to use right now. Yeah, cycle life on LCO right now is 1,000 cycles. It's 750. I guess it depends on how you're testing it too.
Yeah, and it also depends on how high the energy density is. So if I could take a stab at, because actually this was something I really struggled with LCO, because I'm the one that did a lot of that, which is, it is one of the ones that's most used, but when you look at the actual performance metrics, but not maybe the, shall we call them, the long established product lines that make them, maybe it shouldn't be the one that's being used. And that thing is, so this would maybe be the hypothetically, if you could start over and plan from the ground up and look at just the capacity, the capabilities, what you might choose to use. Right. No, absolutely, LCO is still very, very highly used.
You pegged it though. Watt hours per liter is our #1 parameter that we decide chemistries on, and it is right now. We're not using anything less than 700.
Yeah, you got to go good in your pocket, guys. Good for the pocket. That pocket bulge is bad.
Yeah. It is. It is. And so we have to, it's so right now when we look at all the other chemistries that you have listed, when we have the biggest thing is the cycle life and the energy density and swelling. My God, swelling is a huge problem with most of these that we can't tolerate. We have very low swell tolerances. And so right now, LCO is I don't see any other chemistry supplanting it for a long time. Silicon it just grows too much.
It's out.
I can't
for that. Yeah.
I mean, that's not an LCO specific thing, right? Like you look at like silicon's predominantly an anode function, right? So like it doesn't really matter what cathode you pair it with. But like the big problem with silicon is like you look at companies like Enovix who are trying to get into commercial applications, but like the amount of heat generated, nobody likes a hot phone. The amount of reliability of that circuit, the swelling, all those things lead themselves to like a very problematic nature. Now, does that mean there's a world where you can't make that go away through really clever scientific advances? No, but it just means right now, that's not what people are going to be buying because there are, you know.
And hey, Bruce, could I ask you just, I'm sure you can't give specifics, but when you guys basically test something, you want to see 5 or 10 years of cycle life data, right? You don't let somebody get away with accelerated 6-month testing before you put it in a product. So if somebody has not already manufactured something 5 or 10 years ago that you've evaluated and put in your product, it's not going in your product, right?
Right. So just to give you some benchmarks, it takes us 4 years to qualify a cell supplier. That's if we start now. The cell supplier has to demonstrate millions of units manufactured on a consistent line. Somebody mentioned earlier about, you build a battery factory, how long it takes. It takes 2 years for a factory to make anything worth a damn. And there's a lot, like Jeff was saying, there's a lot of scrap that happens. And so we're not going to buy, I'm not going to, put a brand new technology into one of our mainstream products that hasn't had some, miles under it. And so it takes a while for us to qualify, but we're always looking at new technologies, always looking at, trying to get, because I don't want to use cobalt. I don't want to use LCO. I want to use something more sustainable, and I want to, so we're always looking at technologies, but the time it takes to get those companies through that, growth phase and into making, you got to make millions of cells consistently. And that's a huge challenge for a lot of factories. And that's where they spend a lot of time. I can't have a lot to variation.
So we're going to get out of here in 10 seconds. I just want to say something really quickly, which is what you basically just said. It takes 5 years to at least develop a chemistry, 3 years to make a factory. Then it's 2 years for them to get their yields up so that you'll pay attention to them, and then 4 years to qualify. So that's 9 to 15 years.
Exactly. Yep.
Comments, guys. Like the first time a buyer will take you seriously is when you send them 1,000 cells. And they're going to look at them. They're going to look at the tolerances. They're going to look at everything. And then the second thing they're going to do is ask you for 10,000. And then they're going to ask you for 100,000. And then they're going to check it. And that's why the qualification timeline takes so long. And I also want all of you to take this kind of, Aubert and I say this a lot, the battery industry has the complexity of semi, the margins of automotive, and the throughput of paper. And the throughput of paper is what is going to kill you on the tolerances side.
Wow, that quote should be, I don't know, chisel in stone somewhere. That's great.
Can we get a shirt with that? That was great.
Oh yeah, we should have merch. We should have Volta Foundation merch.
I mean, and I want to add something here, but I was in the middle of something. I got disconnected. I mean, regarding the career prospects of the thing, like I've been like in the particular breakout room, we are talking, and I was telling that people are getting hung up on only like we're looking at opportunities like mostly battery manufacturing, or else like mostly EV side. But people are forgetting the whole ecosystem, like recycling, software development, regulatory policy side. There are plenty of jobs there. So we go for the name, and we are like not these employers are willing to go extra mile for you guys. So please look out for the other stakeholders in this ecosystem and apply